Hello dear students, welcome to the channel and welcome to this playlist in which we are discussing about different type of transforms which helps us shift from time domain to frequency domain. So up until now we have seen Fourier transform, Fourier series, we have seen Laplace transform, we have seen the properties of each of these transforms in detail. We've also gone through the discrete Fourier transform and discrete time Fourier transform in very last lecture, and with that we've also uh, discussed the relationship between these transforms. So we discussed the relationships between Fourier and Laplace in particular in detail, and from this lecture onwards I'm going to start the Z transform or Z transform. This is also one of the tools which helps us move from time domain to frequency domain and vice versa. So before I start the Z transform, I would like to tell you that same as previous lectures of this playlist, we will need a lot of mathematics here. So if you are weak at mathematics, please uh, revise your calculus class, uh, reread your calculus books, see the formulas so that you can catch up. And also it will be beneficial if you have better idea about Laplace transform and Fourier transform. So Z transform, understanding of this Z transform will be very easy in such case. So let's begin with the definition. So definition says that if I want to find the Z transform of x of n, which is my continuous time signal x of n, then what I will do, I will take that signal, I will add that signal up from minus infinity to infinity, and I will multiply z raised to minus n in it, and the output which I will get will be the Z transform of that signal x of n. So here you can see the formula for that. Z transform is equals to x of z is equals to summation n is equals to minus infinity to infinity x of n z raised to minus n. We know that z is a complex variable, so it will have different parts. Real and imaginary parts, and this time domain and frequency domain variables xn and xz are called Z transform or Z transform pairs, and we can represent it via uh, this uh, this structure. Now before we move forward, I want to discuss about a concept called poles and zeros in Z plane or S plane. So Z plane is for Z transform and S plane was for Laplace transform. So any transform of a time domain signal which can be expressed in terms of ratio of numerator polynomial and denominator polynomial, like I'm having x of s, talk about Laplace transformation. X of s is equals to n of s divided by d of s. N of s and d of s are numerator and denominator polynomials. So what we can do, we can obtain the roots of the numerator and denominator, and we can represent it via s minus z1, s minus z2, and for numerator, and for denominator we can represent it s minus p1, s minus p2. So this z1 z2 are zeros and p1 p2 are poles. So I bet if you are in fifth semester you must have knowledge of poles and zeros a little bit. I'm just uh, giving you a glimpse to quickly refresh it. so I'm not presenting about it in this presentation. So the poles of my transformed signal, x of z or x of s, are the values of either Laplace or Z transform variable s or z that causes my x of s or x of z to become infinite. And same way, zeros of my x of s or x of z are the values of either Laplace or Z transform variable s or z that causes my x of s or x of z to become 0. So the s plane, uh, in case of Laplace, the Laplace plane consists of an imaginary axis and a real axis. And same thing is true for Z transform as well. So you can represent poles and zeros in this as plane, right? Now let's move forward to the types of Z transform. So basically we can see there are two types of my Z transform: bilateral and unilateral Z transform. So in bilateral, we define the Z transform above both sided summations as we did earlier, like we took minus infinity to infinity. And when we take from 0 to infinity, that is called unilateral or one sided Z transform, right? So we are only taking the Z transform of positive side, and based on different type of Z transforms, we will have different ROCs. ROC stands for region of convergence. So we saw the region of convergence earlier as well for different type of transformations. So in Laplace, what is the definition of ROC? It is basically a region when my Z transform will converge, right? So it is uh, it is clear that Z transform is an infinite power series, and that you can know from definition as well, if you remember the power series back in calculus class. So this series is not convergent at all values of z, and because of that you can use this ROC in the mentioning Z transform. Now what are the advantages or what is the significance of my ROC? So it gives an idea about value of uh, zeros for which Z transform can be calculated. ROC can be used to determine causality of my system as well as the stability of my system. So this way we can find either causality or stability, and we will be seeing that in the sums as well, in numericals as well. Let's consider one numerical here. Let's take the first equation. We have to determine the Z transform of this sequence. You can see x1 here. X1 is 1 2 3 4 5 0 7, and because there is no arrow given here, which means the first value is x1 of 0. So value of x1 is x1 of 0 is equals to 1, x1 of 1 equal to 2, x1 of 2 equal to 3, and up to then it will go till x1 of 6 equal to 7, because we are total having 7 numbers here. Now you know what is the definition of Z transform, right? X1 of z will be summation n equals to 0 to infinity x of n z raised to minus n. But here you know that we are only going till n is equals to 6. So we will take limit n equals to 0 to 6, and we will do the same, like we will perform the same operation. So we will get x1 of z equals to summation n equals to 0 to 6 x1 of n z raised to minus n. Now when we put values in this formula, what we will get, initially we will put the value of x1 of 0, which is basically 1. So 1 into we will put values of n from 0. So x1 of 0 into z raised to 0, right? So the answer will be 1. Then we use x1 of x1 of 1, the value is 2, which means 2 z raised to minus 2, right? Then we will put value of x1 of 2, which is 3, and accordingly we will put all the values, and we will get value of x1 of z, which will be 1 upon 1 plus 2 by z plus 3 by z square plus 4 by z cube plus 5 by z raised to 4 plus 7 by z raised to 6. Now that we have calculated the z transform, then we also found out that x1 of z is equals to infinity for z equals to 0, and x1 of z is convergent for all values except z equals to 0. So what will be the ROC of this for this signal? It will be the entire z plane except z equals to 0, because it is not converging on z equals to 0, except there everywhere it is converging. So ROC will be entire z plane except for z equals to 0. Let's try the same thing for different signal. This time we are taking this signal. Here you can see it is having 1 2 3 4 5 0 7 again, but the signal is starting from 4, which means if my signal is x2, as you can see here it is x2, so x2 of 0 will be 4, x2 of 1 will be 5, x2 of 2 will be 0, and x2 of 3 will be 7. That means the left hand side from the arrows, left hand side values of the arrows will be x2 of minus 1 will be equal to 3, x2 of minus 2 will be 2, and x2 of minus 3 will be 1. Now that you know how far the values are going, now you will also know what will be our uh, what will be the summation limits. So it will be minus 3 to 3 x2 of n into z raised to minus n. We know the values of x2 of n. So initially if we take value x2 equals to minus 3, so we will have 1 into z raised to minus n, so minus 3 will be z raised to 3. Same ways for x equals to minus x of 2 minus 2, we are having 2, so that will be 2 into z raised to z raised to 2. Then 3 into z raised to 1. Same ways 4 into z raised to 0, which means 4, plus 5 into z inverse this time. See, with 5 we will be having z raised to minus 1 or z inverse, because the value of x2 of 1 will be 5, so 5 will be in multiplication, and what is the value of n? It is 1, so z inverse. Same ways we will have x2 of 0 equal to 4, so we'll have 0 into z raised to minus 2 plus 7 into z raised to minus 3. So similarly, whenever you put these values together, you will get the equation which will look something like this: z cube plus 2z square plus 3z plus 4 plus 5 by z plus 7 by z cube. So that's the z transform of your signal. And again this time as well, for z equals to 0, the x2 of z will be infinity, which means the entire z plane is again your region of convergence except for z equals to 0, right? But for z equals to infinity, there is an interesting case. Whenever you take z equals to infinity, your value of x of z will also be infinity. So here the infinity is also excluded in the region of convergence. Now let's try to take the same thing. Let's try to do the same thing for another signal. Let's try my del of n signal. So we all know it is an impulse signal, and what is the formula of impulse signal? It will be 1 for n equals to 0, and it will be 0 for all the n's does not equals to 0. So what will happen in such case? Let's try to figure it out. Now we know that it is starting from 0, so you can change the limit. You can take the limit n equals to 0 to infinity delta n z raised to minus n. So what is the value for all the values except for n equals to 0? It will be 0. So everything will be 0 except for uh, x of 0, which means x of 0 into z raised to 0. You know what will be the value of z raised to 0? It will be 1. What is the value of x of 0? It is also 1, which means the z transform of your delta function or z transform of your impulse function, it will be 1, and that's what they have shown here. The z transform of your impulse function, it is 1. So what will be the ROC of my impulse function, z transform of my impulse function? ROC will be the entire z plane, right? It will be entire z plane. Now we have an interesting case here. Let's try to find the z transform of my unit step signal. We know the unit step signal will be 1 for all the values of n greater than 0, greater or equal to 0 in fact, and unit step signal will be 0 for all the values of n less than 0. So when we substitute in the formula of z transform, uh, when we substitute the unit step signal in the formula of z transform, what we will get, we can change the limit, by the way, because we know it goes from 0 to infinity, so we can take the limit 0 to infinity. You know what is the value of u of n for n greater than equal to 0? It is 1. So you will take 1 into z raised to minus n, which means basically what we will get, 1 plus z inverse plus z raised to minus 2 plus z raised to minus 3 plus z raised to minus 4, and it will continue, right? So it will continue till infinity. And when such things happens, we can use this formula 1 plus a square plus up to it is always whenever we take the sum of such kind, the equation will always end up with the final formula a divided by 1 minus a 1 minus a dash, sorry. So the final formula is a divided by 1 minus a dash. So we are having this similar situation here. So what will be our final formula? X of z will be z inverse divided by 1 minus z inverse dash, and value of it will definitely be less than 1. Why it will be less than 1? So see, the z inverse less than 1 is equals to z greater than 1, correct? So what is this condition, z greater than 1? It's nothing but ROC of my x of z. So the z is representing a circle in a z plane, and this circle is having radius of 1 here. Whenever I say that z is greater than 1, which means I'm having a circle in a z plane, and its radius is equals to 1. So whenever I take z greater than 1, it indicates area outside the circle. Okay, it only indicates the area outside the circle. So in this figure you can see the shadowed area, which is for z greater than 1, and it is the area outside circle, and z less than 1, it will be the area inside the circle, and z equals to 1 will be the circumference of this uh, circle, right? So uh, what does this image tell you? It tells you that the x of z is convergent in the whole area for z greater than 1. So the circle of radius is 1, and hence z will be 1, and the z will be called the unit circle. This circle will be called the unit circle in z plane, but the imaginary values can be plotted with respect to real values as well in z-plane. Remember, initially when we started discussing about z transform, I told you that z transform is actually a complex entity. It is complex number. So similarly for my similarly similar to my delta function, the unit step functions z transform will be 1 by 1 minus z inverse, and the region of convergence will be all the z greater than 1. So all the values of outer plane outer plane of this circle, right, will be the convergent point for z equals to 1. Now let's see one more. This time we will take x of n equals to a raised to n u of n. We already know the formula of u of n and how does it converges. So we are going to use it here, and we are going to use a raised to n as well, right? So let's put this formula into the formula of z transform. So you will have summation n equals to minus infinity to infinity a raised to n u of n into z raised to minus n. Now since the u of n is only exist in the right hand side of my origin point, so we will avoid all the negative values. So we will go for the limit will change. It will be summation n equals to 0 to infinity a raised to n z raised to minus n. Remember, we are not mentioning value of u of n as well here, because your value of u of n is 1, and if you don't mention 1, it is okay. Notice one more thing here, both a and z are having common n power, so we can take it out common, and we can base the formula based on that, which will be equal to 1 plus az inverse plus az inverse whole square plus az inverse cube plus az inverse raised to 4, plus it will continue, right? It will continue till infinity. Now this situation is a little bit similar to my unit step functions situation, except we are having a in multiple with z. So what we will do, we will simply use the same formula, and this time we will keep this multiple intact with my z transform. So the final formula will become a into z inverse divided by 1 minus a into z inverse, right? Now what does this formula tells us? It tells us the value of a into z inverse is less than 1, which means the value of the value of z minus a will be greater than 0, which basically means the value of z is greater than a. So this time it is little bit similar to unit step function here as well, except in unit step function the radius was 1, but this time what will be the radius? So radius will be a, and all the area outside of this radius a will be the ROC of my signal, and the area inside a will not be. So the all the shaded part you can see here is for z greater than a, and it is ROC, and all the circle and its radius, it will be z less than a, and it will not converge. So the final formula is 1 upon 1 minus az inverse. Now let's go through some properties of my region of convergence. It is very important in terms of z transform. So let's see what is the first property of my ROC. So the ROC for finite duration sequence will include entire z plane except for z equals to 0 and z equals to infinity, which we saw earlier as well, right? In the very previous sum we saw the proof of it, so I'm not discussing the proof in detail again. Second property is ROC does not contain any poles. So in the very last in very last derivation of a raised to n into u of n, we saw the proof of that as well. The function has pole z equals to a in this case, because x of z is equals to 1 z upon z minus a. So the function of pole at z equals to a. So my function is having a pole which is z equals to a, but note that in ROC z is always greater than a. What does it mean? So it means poles do not lie in the part of my ROC, and actually x of z equals to infinity at poles by definition of pole, right? So that's your second property. Third property is ROC is the ring in the z plane centered about the origin. Okay, so it's always centered around the origin, because we always took that way. So let's try to prove it. We will take the same example again, same example of very last example. We are having the signal a raised to n into u of n, and when we are doing the z transform of it, and we obviously derived the value 1 upon 1 minus a z inverse. We also know the ROC, it will be z greater than a. So here the z or z is always a circular region which is always centered around the origin whenever we calculate it. Fourth property is ROC of causal sequence is of the form z greater than r. And for this let's take the same example we discussed a few minutes ago. Let's consider a right hand sided sequence of a raised to n into u of n. So the ROC of this sequence will be z greater than a, and we know that what is ROC, it is z greater than a. So ROC of right handed sided sequence will be in the form of z greater than r. And what is the r? R is basically radius of my circle. The fifth property says ROC of left sided sequence is of the form of z less than r, and based on fourth property it makes sense, right? We are, instead of a raised to n u of n, let's take minus a raised to n u of minus n minus 1. So its ROC will be z less than 1, which means the inside of the circle part, right? And when we have inside of circle part, z will be less than r. Sixth property says ROC of two-sided sequence is the concentric ring in the z plane. Concentric ring in the z plane. Remember we discussed about the circumference of z plane. We are talking about that z plane only. So when we take the z transform of this signal a raised to n into u of n plus b raised to n u of minus n minus 1, what we will get, the z plane will be between a and b, which means a less than z less than b, which means we will get a concentric ring of my convergence of z transform. So that's what this property is saying. Seventh property is, if x of n is finite causal sequence, then its ROC is the entire z plane except z equals to 0. And we have seen the proof of this as well earlier when we discussed the very first numerator. The eighth property tells us the ROC of stable LTI system contains unit circle in the z plane, right? And we will prove this property in upcoming lectures when we discuss about the properties of z transform in particular, and even later on when we discuss about the inverse z transform as well, because you will need the knowledge of inverse z transform in order to understand this. So I'm not proving this property right now, but later on we will discuss about it. The ninth and final property says the ROC is a connected region, and this is something you must have felt whenever we discussed about ROC, because you will not see that, oh, I'm having one ROC here and then I'm having two ROC few points away, right? It's ROC, it's not poles and zeros. It can be only at one place. So the convergence of sequence which exists over a certain area rather than discrete points, and because of that the ROC is connected region, right? Because it is convergence of a sequence, not one point. So these were the properties of ROC, and I think we will keep this lecture till here. In the next class we will be discussing about the different types of properties of Z transform. If you have any doubts or any queries related to today's class, or if you have any suggestions for channel, please feel free to mention them in the comment section below. I will try to answer them as quick as possible and as many as possible. So I will be seeing you next time. Till then, take care of yourselves. Goodbye, and thank you very much for listening.